This video is going to go through some examples using Stokes' theorem. So this first one, I didn't feel like writing a paragraph for you, so I summarized it all visually. So here we still have our unit, or our upper hemisphere from the unit sphere oriented outwards, so imagine that's a sphere and all that good stuff. And then we have the boundary oriented consistently with the surface orientation. Okay, we have our vector field, and we want to find this expression. So we want to find the vector surface integral. And so this vector field wasn't as nice as the previous one, so doing the curl, it looks like it's a chore, so I don't want to do it. So I'm going to use Stokes' theorem, and I just need to make sure that we are able to apply Stokes' theorem. So S is bounded, piecewise smooth, oriented surface, okay, and the boundary does consist of finitely many piecewise continuous, simple closed curves. So I can apply Stokes' theorem and just say that this whole thing is the same as the closed integral over the boundary of f dot ds, and we found this in the last video. We parameterized it, and so if you need the parameterization, look there. I'm just going to jump right to the surface or the integral, so we get 0 to 2 pi, and then when we do the composition here, it'll be cosine t. Oh, I'm sorry, that was from the last video. So if we look at f of x of t, and I'll get my vectors going, dotted with x prime of t dt, what we end up with, and I'll let you verify this, is negative cosine t sine squared t dt. And so with this, we can do a u substitution. U is sine t, and du is cosine t dt. So then we end up just getting, so let's see, this will be u squared du, and I have a negative in here, and then when I put in the boundaries, well, that's going to be 0 to 0, so this is just going to be 0. Oh, that's interesting. Okay, so there you go. We can use Stokes' theorem in reverse. So rather than just using, rather than using the line integral around the boundary, we can just look at, instead of looking at the vector surface integral, we can do the vector line integral over the boundary. Okay, and so example 2 here is kind of a little bit more fun. At least I think it's more fun because we deal with a different shape. Okay, so here S is our chef's hat that is smooth, okay, and these little lines in back here, don't worry about them. That's just to add dramatic effect, as it were. And so we have this oriented in such a way that we have an outward pointing normal, and it's above the unit circle, ds, and ds is consistently oriented, okay, as you can see here, and we want to compute the curl. Or sorry, we want to find the vector line integral, which involves the curl. Okay, so then we can, again, by Stokes' theorem, okay, we have to go through and verify, okay, do we have a bounded, piecewise smooth, oriented surface? Yep, yep, yep. And the boundary consists of finitely many piecewise C1 simple closed curves. Yep, yep, yep. So then we can say that this whole thing is really just the integral over the boundary of S of f dot ds, and by the previous example, when we did this calculation, that's where we got the negative, so we got negative cosine of cosine t sine t, or sine squared t dt, and well, after some work, we just found that that was 0. So that was a little disappointing, actually. So we can, again, use Stokes' theorem either way. We can look at, and I forgot to add over the surface. We can look at it, a vector line integral over the surface, or we can look at the line integral over the boundary. Okay, so as you can tell, this is seeming very similar to what we did with greens. We looked at a line integral over the boundary and compare that to the area, right? So now we're talking about kind of the same things, just different dimensions. So in the next video, we're going to compare the two and go on from there.